So welcome back to our second talk. Our second talk, the speaker is Loseu. So he is going to talk about quantizations of nilpotent orbits and Lagrangian subvarieties. So let's welcome.
Thank you, guys. Thank you for the invite. Let me give you a plan of this talk. I'm going to talk a little bit about Harish-Chandra modules. I'll then go and talk about quantizations. Conical symplectic singularities. And finally, I'll talk about quantizations of Lagrangian subvarieties. Okay. So let me explain a setting first. The first part, G is going to be a semi-simple reaction over the complex numbers, and I want to fix an evolution of the cell. And by this I mean the algebra. For instance, there are the following examples. So I can take G to be SLN, and I can take sigma to be x goes to minus x transpose. I can take G to be the direct sum of two copies of the same algebra, and then I can take sigma the permutation of the n. And what we care about in this setting is a fixed point of this involution sigma. So the fancy letter is meant to be German K, going to be the fixed point locus. In my first example, this K is SON. And in my second example, K is just G0 embedded back. And then I care about the following class of representations of G. A Harish-Chandra GK module is a finitely generated module of the universal enveloping algebra with locally finite action of this subalgebra K. What this means is that you can include every vector into a finite dimensional K stable something. Okay. So here is a little example. Take the universal enveloping algebra. This condition certainly does not hold, but it does if I model out the left ideal generated by K. So this module here is Harish. And well, the notion is due to surprise, surprise, Harish-Chandra. What he cared about was the following question. So Harish-Chandra wanted to understand infinite dimensional representations of real Lie groups. And from this data, I do have a real Lie group. So real structures on G correspond to this involution. So I want to care about unitary representations of the corresponding real group. versus irreducible Chandra modules. And one can actually produce such a reducible representation out of a reducible unitary representation, so that we essentially have a. And that's a very classical object representation theory, and kind of the classification of such reps becomes a question of which reducible Chandra modules come from unitary representations. Now, what I want to start in this talk is something else. So here I also see it as quantizations of certain Lagrangians. At some point, I will explain what this means. And there is an optimistic hope that the image of a reducible unitary representation sits here for some groups. Because the adjective here is closure state. For example, all complex groups, which are viewed as real groups, are closure state. Okay, so that's kind of some motivation. Now let me get to the second part, which is about quantizations of conical symplectic singularities. So I'll start by explaining what I mean by a quantization. So I will start with curly A, which is going to be a fielded associative function. Right? You know as a complex numbers. Well, fielded means that it comes with an ascending filtration by subspaces. Okay. And I'm going to assume that the associated graded algebra group of A is commutative. So when I have an algebra filtration, it means that an element of degree I and an element of degree j, when multiplied, live in degree I plus j, and this condition means that the Lie bracket will actually live in degree I plus j minus 1. And once you have this, and it gives you a Poisson bracket on the group of A by the following formula. So A plus elements of lower degree, bracket with B elements lower degree, it's defined to be the Lie bracket of A and B. So this has degree I plus j minus 1 plus elements of lower degree. And then I say that study A is a quantization of the associated wave function. And of course, the classical example is that the universal enveloping algebra is a quantization of the symmetric algebra of G. So this comes with a filtration by degree in G. This is a graded algebra and has Poisson bracket used by the Lie bracket of the algebra. Okay, so this statement is essentially Poincare-Bergolf-Hitzius. Now, I will be interested in quantizations of certain Poisson algebras, and these are my conical symplectic singularities. And because of time constraints, I'm not going to give a definition of what it means to be a symplectic singularity. I'm going to give you an example. And that's essentially the example that I'm going to care about. So I want to pick a nilpotent orbit in my algebra. For example, if this algebra is a classical one, like SL or SO or SP, it just means an orbit of the group G consisting of nilpotent matrices. Okay. And then what I care about is algebra of polynomial functions on this orbit. So this orbit is a smooth variety, but it's not a phi. Okay. So what can I say about this algebra? Well, this algebra is graded. The grading comes from the dilation action of the one-dimensional torus here. Okay, so every nilpotent orbit is stable under dilations. This algebra is Poisson. Every orbit in G is a symplectic variety with respect to Kirillov constant form. And this algebra is finitely generous. And so what I can do, I can form the spectrum of this algebra of functions. It's going to be an affine singular Poisson variety. And it turns out that it has symplectic singularities, meaning that while it's singular, the singularities are still nice. And well, I also have the word conical. Conical means that the action of the one-dimensional torus contracts this variety to a single point. So it's a cone. And this is a class of, so that's a class of graded algebras that I'm going to care about. Quantizations I'm going to consider. In fact, you can do it a bit more generally. You can replace orbit O with its equivariant cover. But again, due to interest of time, I'm not going to talk about this picture. And then basic questions that I could try to ask. Okay, so I have this graded Poisson algebras. Can I classify the quantizations in the sense that I explained above? So let me state the results. Classification theorem. There is a bijection between quantizations of the algebra of functions on X, which in my example is the same as the algebra of functions on O, and points of a finite dimensional vector space, which I will call H sub X. So it's just finite dimensional vector space. I will give an example a little bit later. Let me just point out that this is a slight lie. I mean, this talk will be filled with slight lies. That's a lie because most naturally this space arises with a quotient of a vector space by reflection. Of course, when you model out a reflection group, you still have the same variety. So it's only a slide. We'll see it in an example. And let me introduce notation for a parameter lambda. The corresponding quantization will be called A sub 1. And so what kind of algebras are we going to get? Let me make a remark about that. So let's still take our X to be the spectrum of functions on the nilpotent orbit. And in particular, notice that on the spectrum, I still have an action of the group G. Okay. And this action leads to a quantization. So we have an action of G on A lambda. Moreover, you have a homomorphism from this S of G to the functions on O, because O maps to G. O just is included into G. And this also deforms. I also have a homomorphism from U of G to A lambda. Homomorphism is G equivalent, so-called quantum common. It doesn't need to be surjective, but it's not that far from being surjective. So the thing is often surjective. And so essentially, I'm dealing with certain quotients of the universal enveloping algebra. But in any case, the application to Lie representation theory is as follows. I could try to study some representations of this guy in geometric means. And then, of course, every representation of a lambda can be pulled back to the universal enveloping algebra. And that's what I'm going to do. So I promised an example, so let me give you one. So I will take O to be the principal important fact. For example, if we are talking if we are talking the algebra SLN, that's an important orbit corresponding to single order. And then the orbit closure is just the important cone. The variety of all important elements, and it's normal, so that's my x as well. And it's easy to construct a bunch of quantizations of this x. And they'll look like the following. I take the universal enveloping algebra U of G, and I model out the ideal generated by a maximal ideal in the center. Now, how does the center look like? It looks like while group invariant functions on the Cartan. Okay. So in particular, my quantizations are classified by points of the Cartan modulo the one. My H sub x here is just Cartan. Well, more canonically, it's dual of the Cartan. In particular, you clearly see these structures. So the action of G is induced from the universal enveloping algebra, and this homomorphism is always a surjection. It's surjection in this. Okay. So let's get to the main part and talk about quantizations of Lagrangian subvarieties. And I want to start by defining the notion of a Harish-Chandra module in the general context of quantizations. So for this, let me introduce some setting. So my A here is a field algebra. For now, it's a field algebra S in the beginning of section 2. And I want to come with an additional structure. The structure we call theta is going to be an algebra anti-involution. Well, it's still an involution. The square is equal to 1, and anti means that it sends products with a product in opposite pair. It's anti. Let me give you examples of the situation. Example number 1. So let me take G and sigma like in the very beginning of this talk. And then, well, sigma is a Lie algebra involution. It's very easy to convert it into a Lie algebra anti-involution. Let me put theta to be equal to minus sigma on G. And then I can extend this theta to an anti-involution acting on the universal envelopment. That's one example. Another example, let me take A to be the tensor product of two copies of the same algebra, where the second copy comes with opposite multiplication. And then I have a anti-involution which will send A tensor B to B tensor A. It's another example. So now, in this setting, I can define the notion of a Harish-Chandra model. So let me do it in several parts. So first, let me define the notion of a good filtration. On some A module, which I call M. So it's a filtration by subspaces. It's also an ascending filtration. I want it to be compatible with the filtration of my algebra. I want the product of A less or equals than I and M less or equals than J to be M less or equal than I plus J. And good refers to the condition that the associated gradient for this filtration is finitely generated name. Okay. That's a classical theorem that in every finitely generated A module there is such a filtration. Now I want to consider filtrations with an additional condition which has to do with this anti-involution theta. And it's the following. So if I have my element A in filtration degree less or equals than I, and this element satisfies theta of A equal to minus A, then A maps M less or equals than J. Well, this condition here says that it will be in degree less or equals than I plus J. I want it to be in degree less or equal I plus J minus 1. So if for all A, this condition is satisfied, then I say that my filtration is compatible with theta. And then I say that M is Harish-Chandra, A is theta module, we could admit such a filtration. A good filtration compatible with. And of course, you can ask what is the motivation for this definition? Well, let me explain what happens in the setting of example number 1. So in example 1, a good filtration is compatible with theta if and only if it's case stable. It's a nice exercise, but let's see one direction. So let's see. K is fixed points of sigma, so it changes sign under theta, and it lives in degree 1. In particular, if I take A from K, then I see that M less or equals than J goes to M less or equals than J. Okay? And so this filtration is automatically K stable. You can go in the other direction. So the Harish-Chandra usually theta model is the same thing as Harish-Chandra GK. And what I've done, I've generalized definitions that I had before. All right. So now, let me explain what this has to do with quantizations of Lagrangian subvarieties, which I had at the time. And it's based on the following observation. So the associated gradient of theta is anti-Poisson involution of the associated gradient of A. I always want my theta to preserve a filtration, and then if you look at the formula for the Poisson bracket, you see that every algebra anti-involution should give you anti-Poisson involution. Okay. And now let me specialize to the setting when this A is the algebra of functions on a conical symplectic singularity. In particular, symplectic singularity implies that the regular locus of X is symplectic. So just kind of having symplectic singularity is the right analog of being symplectic, but for singular varieties. For the smooth part, you should have something honest. And if you want to, so let me take Y to be the fixed points of theta in X. And then a basic observation is that the intersection of this Y with X rec is just honest Lagrangian separate. So it's smooth Lagrangian separate. It's a consequence of having an anti of this being an anti-Poisson equation. All right, so now what does this have to do with Harish-Chandra modules? Is the following observation. So if I take M, the Harish-Chandra A theta module, then first of all, and that's an easy exercise, the associated gradient with respect to any compatible good filtration is supported on Y, on the fixed locus of theta in X. And moreover, if you restrict this module to X rec, the smooth part, then what I get is a push forward to X rec of a twisted local system. On Y intersected with X rec. Okay. And as an optional remark, you can actually read the twist from the quantization parameter. If your quantization parameter is 0, then you have half harmonic. And so in this sense, Harish-Chandra modules are quantizations of the singular Lagrangian Y together with a twisted local system on the intersection of Y with the smooth locus of X. So that's kind of the object that I want to consider. So now, what would I want to achieve? I would like to have a classification of irreducible Harish-Chandra modules. And now, from a Harish-Chandra module, I'm able to get some geometric data. This data is a data of a twisted local system. So you could ask, can we classify Harish-Chandra modules from this data? Question 10 will cover. Irreducible M from M restricted to X, which is some geometrical. And in order to do this, we need to impose an additional assumption. The assumption is going to be that the codimension in Y of Y without X rep is big or equal than 2. Okay. So somehow, by going to the smooth part, I removed relatively little. I removed something of codimension 2. And kind of the basic statement that goes into this assumption is that, if you have a vector bundle on a reasonable variety, and this vector bundle outside of codimension 2, then you know it everywhere. You can just push forward. On the other hand, if you know it outside of codimension 1, then you don't know much. Outside of codimension 1, it will be just trivial or suitable codimension 1 subvariety. Okay, so that's our question, and let me try to give you some statements along the lines of yes, we can. So people old enough to remember what this means. How this was used back in the day. So I'm going to state something that I call Symmetry theorem that appeared in various cases. Perhaps the most general is a paper by Long and Yu from 18. So essentially means that perhaps you need to impose some technical assumptions to make it work, but in all situations that you're actually going to care about, these assumptions are satisfied. Okay. And so essentially theorem says the following. It's kind of nice to, to make some bullshit statement and attribute it to other people. Okay. I play some role in this kind of result. So first of all, if M is irrefutable, then so is this twisted local system. And moreover, the twisted local system recovers M unique. So somehow, a slightly imprecise way to think about it is that you actually have a functor going from the category of Harish-Chandra modules to this category of twisted local systems, and this functor is basically fully phased. It's actually a theorem in some cases. Okay. So then, of course, in its general result, you can ask, does any twisted local system?
Ivan,
yeah.
The second statement also require irreducible or not?
Yeah.
Okay.
Look, I mean, I'm sweeping a lot of things under the rug, and I'm not responsible for the subsequent cleaning of this rug. Okay. Well, Harvard is a rich institution, and it can afford cleaning
I
charges.
think Leon is going to be giving a talk.
And I will be gone by then, so and he's by Zoom. So I want to finish by talking about existence results. And it's about the question for which twisted local systems there is a context. So here, kind of the story is much less complete, but there are answers in at least two important special cases. So special case one is this.
So here you mean like when you can find a corresponding module?
Yeah, there is a quantization M with, who's
With this condition.
with this condition.
Got it.
Special case one is this diagonal case. I have some quantization A0, and my A is the product of A0 and A0 opposite. So of course, my variety X is going to be the product of the corresponding X0 with X0 opposite. And my Y is just diagonal copy of X0. And certainly satisfies this condition because, well, I mean, another condition on singular symplectic variety is the codimension of the singular locus is bigger equals than 2. And in this case, the result is due to myself is, and I don't have time to state it, that almost always we can recover, so we can just completely describe these quantizable locals. I need twisted because in this case there is no twist. Okay, so just almost local terms, they correspond to representations of the fundamental group of this X rack, and this fundamental group is finite. And depending on the quantization parameter, we can say which representations of the fundamental group give rise to Cauchy-Chandra models. For example, if quantization parameter is equal to 0, called harmonical quantization, you look at the following option. So this variety X rack is going to have codimension to this variety X is going to have codimension to these because they don't stay outside of the regular ones. And you look at all local systems which don't have monodromy around those leaves. Okay, so that's some geometric condition. And almost means the following. So I need to care about dimension 2 slices in X, and I don't want them to be of type E8. This happens, but it happens very rare. Okay, so I guess I still have like what, 5 minutes? Oh, around 5 minutes. So let me tell you about another special case. We know zones, huh? And this is joined with Lagrangian. Let's in preparation. If the quality of the paper were determined by how long it was in preparation, like like with wine, this would have been a very good paper. It's still a good paper. And so this is in the setting of nilpotent orbits. And I want the condition that the codimension of the boundary of this orbit is bigger or equals than 4. And then my A is a quantization of the algebra functions. And then my theta comes from minus sigma. So it's classical setting of Harish-Chandra modes. So then, if I intersect Y with O, it's classically known. I get is a disjoint union of orbits of K. So this capital K is the connected component of fixed points of sigma in G, symmetric subgroup. And the condition kind of, this condition here in particular implies my codimension condition on the singularities of Y. So this Y intersect every G orbit at a Lagrangian subvariety. And so once I know that this codimension is big or equal than 4, then kind of the codimensions of boundaries of K orbits are going to be big or equal than 2. And so in this case, so the result can be stated like this, is that every K equivalent twisted local system on every of this K orbit is quantizing. So for every K equivalent twisted local system, I can find a Harish-Chandra mode corresponding to this local system. That's not a complete answer because not every twisted local system will be equivalent with respect to K. What you're going to get in this case is that they're equivalent with respect to some cover. And if you go to covers, so if you just work with K equivalent guys, they correspond to representations of real algebraic. And if you want to go to covers of K, this will correspond to representations of nonlinear covers of groups. So when you go to covers, the statement is no longer true. There are some twisted local systems which will be missing, and that's kind of a new phenomenon compared to kind of here, not every local system is quantizable, but somehow quantizable one correspond to certain quotients of to representations of certain quotients of the fundamental. And somehow in this setting, this is no longer. So it's not complete. But we can in many cases say which twisted local systems are quantizable. Right. So that's the end of this imprecise and misleading talk. Thank you for attention.
Are there any questions?
So codimension 4. Does that actually happen?
Yeah.
Can you give me an example?
So let me give you a nice example. I mean, it's your birthday, so you should get nice things. So there are these two distinguished examples. When I take O to be O minimal in SL3 or SP4. So in both cases, the dimension of the orbit is equal to 4, and the only orbit in the closure is 0. In fact, this guy, this O minimal in SP4, you can describe completely. It's you take the vector space C4, you remove 0, and then you mod all the way plus minus. So why am I giving you these examples? Because they're nice in the following fashion. So if you, sorry, it's a, there are like a lot of graduate students in this room, and I'm only showing them bad examples. one bad example, one bad habit that a speaker may have is to start answering questions that they want to answer, but they not the questions that they were asked. Okay. So it's a nice example because kind of this example actually controls a general situation in the following sense. So if you take an orbit in a generic orbit in this complement and you take a slice, in most situations this will look like the closure of minimal nilpotent orbit in SL3 or SP4. So somehow understand in this case it's distortion. But yes, you can actually, back to the question that you asked, yes, it happens often. You can completely classify when this happens. For example, for the algebra SLM, nilpotent orbits are classified by partitions. And the condition on the dimension just means that the adjacent parts differ at most by one. Of course, you can say that more often the opposite happens, and that's indeed the case. Unfortunately, when this dimension is 2, there is very little control over what happens with Paris Chandra.
If under these assumptions, you didn't see how the module ending.
So here, well, I mean, in this setting, I can, well, I mean, okay, so how is this constructed? So let me explain what happens in this setting, because it's somehow more explicit. So you take the simply connected cover of X-ray, and then you take the algebra of polynomial functions. So let's say that somehow you manage to quantize it. And then on this quantization, which often happens to be canonical, you will have the action of the fundamental group by homomorphisms. And then the modules that you get are just as the typical components of this section. Okay. So that's a construction. In general, what you can say is this. So you can quantize your twisted local system on the smooth locus. You will get some module over deformation quantization. Then you're going to take the global section. This is not an explicit construction in any reasonable way, but you can still read a lot of problems.
Do you know which one of the trajectory and the equation?
So, and I'm again going into this version. So, there is kind of, there are known and trusted ways to construct unitary representations, which are basically constructed by some kind of unitary induction or by some kind of differential, also known as matrix. It's a general expectation that somehow you do it while you can, in some sense. So the kind of the classification answer is close to be the most economical answer that you can get using these operations. And then my speculation from the very beginning that unitary representations in the quasi-split case should correspond to this quantization is to some kind of quantizations is that this unitarity preserving operations will also preserve being a quantization of a singular Lagrangian. It's not a precise thing. So the answer is yes, we have an idea, but the idea is very classical and goes back to Logan and doesn't have to do with this. So somehow this quantization approach, it tells you several things, but at this point at least doesn't tell you directly which of the modules are interesting.
This is on the geometry side of problem. The different problem about the different kind of function, harmonic function, and other things. Those has analog in the geometry setting?
They do. So the cleanest case is when you deal with complex groups, when there is essentially only one kind of induction. This there is classical parabolic induction, and then there is Zuckerman's cosmological induction for complex groups, they're the same. And there is a very clean answer. You essentially do some kind of Hamiltonian reduction, some parabolic induction, which is a special case of Hamiltonian reduction. For real groups, this is more complicated. Kind of my intuition into how these inductions appear geometrically is that I think the usual unitary parabolic induction has to do with quantizing something in deformation, and cosmological induction has something to do with quantizing things in resolution. Singularities. So you start with a singular symplectic variety, and there are two things that you could try to do. You could try to deform it. You could try to resolve it. Of course, you want deformations compatible with the Poisson bracket. You want resolutions compatible with the Poisson bracket, and both things improve your singularities. Okay. And somehow, when you do it for the variety itself, well, I mean, a physicist would tell you that deforming and resolving is more or less the same thing, and it's true in some sense. When you do it for Lagrangian subvarieties, somehow you get difference. And maybe I don't know, am I allowed to give a public extended answer to the chat's question? So you already kind of see it when you deal with quadratic cone. Name and all men, so let me try to recall the equation. I think it's ABC. Condition is something like b squared is equal to AC. And then you have your favorite Lagrangian. The favorite Lagrangian is b equals 0. If it's not your favorite Lagrangian, I urge you to reconsider. And this Lagrangian is just a union of two lines. Looks like this. So there are two ways how you can smoothen this Lagrangian. You can deform. So if you deform, then this Lagrangian becomes, well, I mean, everybody who taught, I don't know what, Polish level math knows what it refers to. That's a smooth thing. It's an algebraic torus. And when you resolve, well, your resolution is T star of P1, and then these two guys become cotangent fibers to the north and south pole. They kind of become this. Now, things that you could do, well, I mean, we are not good in quantizing this kind of Lagrangian because the dimension of the boundary is 1. We are fairly good with quantizing this kind of Lagrangian, which is smooth for this kind of Lagrangian. Then you can quantize them separately, and you can take global sections. That's a very clean procedure. So here, what you do is quantize, and then you degenerate. Generation is still, it's not well defined on the level of modules, it's well defined on the level of case theory. So you at least get some case theory classes. And this corresponds to, well, this corresponds to usual parabolic induction, this corresponds to homology.
On the question of unitarity, I mean, naively, the only way I know how to decide is to compute signature, right?
Yeah.
So, but they're hardly effective, right?
That's
right. Even if you know the module, it's still solving.
Well, I mean, there are bounds, and you can feed your module or some parameters for a module to solve it. Plus, it will tell you what its unitary.
So, I mean, this program of using quantization to answer unitarity, it's still kind of like tenuous, right? It's like a tenuous hope. Yeah. At the end, there are no effective way to write your signature.
And well, I mean, there are computationally effective ways, but I mean, this program doesn't tell you.
If no more questions, let's thank the speaker again.